Perfect ionic model and born-haber cycle. Let's first recap. What's a born-haber cycle? Born-haber cycle is a thermochemical cycle used to calculate the lattice enthalpy of an ionic compound. It's based on the Hess's law, where the total enthalpy change is the same regardless of the route taken. It involves the formation of an anionic solid from its elements in standard states. So when we construct Born-Haber cycle, we start off with the ionic compound, which is, for example, sodium chloride. And first of all, we involve the enthalpy change of formation, standard enthalpy of formation for the sodium chloride from its element in their standard state, which is solid for sodium and gas for chlorine. And then we move up to get the atomization enthalpy for sodium from solid to gas, and then the atomization of the chlorine to change it from chlorine as a molecule into chlorine gas as an atom. And then moving up to the first ionization enthalpy for the sodium to give the sodium ion, and then the first electron affinity for the chlorine to give the chloride as a gas, chloride ion as a gas. Now we reach to the point where we have the ions, the gases of the ions, and they will form the product, which is the solid sodium chloride or the ionic compound. And this is the lattice enthalpy for the formation of the sodium chloride. So what is the perfect ionic model? The perfect ionic model assumes that ions are perfect spheres. They are point charges, and only electrostatic attraction exists between these ions, and there is no covalent character or polarization. So when we assume a perfect 100% ionic character for the ionic compound, these are the ion perfect spheres, point charges, only electrostatic attraction, no polarization or covalent character. So why might the experimental and theoretical lattice enthalpies differ? Theoretical values assume perfect ionic bonding, while the experimental values, the values that we get from the Born-Haber cycles, are often more exothermic. There is discrepancy, and this discrepancy suggests that there is some covalent character for the ionic compounds, and ions are polarized, especially when we have small, highly charged cations like aluminium. So ions with covalent character would look like this, where, as you can see, that the positive ion has caused polarization of the negative ion or of the ionic or of the electron cloud on the negative ion. So there is more polarization now, and there is some of the covalent character, and they would need more energy. So the enthalpy of the lattice now is higher or is more exothermic. Polarizing cations distort the electron clouds of the anions, as we said, and anions with large size and high charge, like iodide, are easily polarized. So that leads to partial covalent bonding and greater lattice enthalpy than the predicted from the theoretical values. So let's have a look at this table that compares between two ionic compounds. One of them is sodium chloride and the other one is silver chloride. Sodium chloride, the difference between the theoretical lattice enthalpy and the experimental lattice enthalpy is quite small, while for silver chloride, the difference here is quite large. So that suggests that sodium chloride is close to the ideal or the perfect ionic model because there is a small difference between the theoretical and the experimental values. While for silver chloride, there is a significant covalent character because there is a large difference between the experimental and the theoretical lattice enthalpy. So this is because silver ion polarizes the chloride more than the sodium ion. So there is more of the covalent character. Exam tips, they might ask you in the exam. So they might ask you to explain why the experimental values for the lattice enthalpy is greater than the theoretical value. They might ask you to state the assumptions made in the perfect ionic model, and they might ask you why does compound X have a larger discrepancy between the theoretical and experimental lattice energy than compound Y. So the tip here that